Okay, hi. So we are continuing with class number 3, the spectral analysis Fourier transforms were covered in the last lecture. And besides the fact that these are powerful tools to be able to analyze signals and find out their underlying frequency constituents and properties, and that the Fourier or frequency representation has certain more intuitive meanings or physical representations that make sense that we cannot see directly from the waveform. It also, the ability to work in a different domain, in the frequency domain, was also very useful for a lot of engineering purposes. So let me cover a little bit about filters and the convolution theorem. And I think I was kind of trying to pick topics which would be the highlights of signal processing, just because these concepts reappear and reoccur as we're going to move really next week to statistics and machine learning. Somehow this whole week, except for some motivation that hopefully I'll get to, talking about randomness and composing music, and a little bit of noise as a random phenomena in signals. This whole week was devoted to actually representation and the type of data that we encounter in music and machine learning. So we can just move a little bit here, the bars. Linear filters and convolution theorem. Okay. So one thing, and this is optional because we had a lot of equations before, but what I want, the basic take-home message from this slide, I wanted you to know that there is this concept of Z transform. It is basically kind of a generalization or extension of the Fourier transform. So you don't need to really know what Z transform is, besides the fact that knowing that, if we replace the Z here with exponent with J and omega, or J and 2 pi divided by N with some K. So this Z will be replaced here with a K, but the Z itself will be this, right? So if you kind of just visually look at this analogy, and the Z transform usually is, or the standard definition really assumes that you have infinite series. So there are quite a few technical differences, but conceptually, I would say a Z transform, because most of the time our Xn will be finite anyway. So the definition is with goes to infinity here, and here we explicitly know that it's a finite duration. But besides this fact, if you think about Z as a complex number, then Fourier transform is a private case of Z transform, where your Z is e to the power of minus j2 pi k divided by n. So just the index here is k, because this is a specific selection of points Z on the unit circle, while this is any number Z. So you can think about this a little bit as a way to kind of generalize. Instead of going on the unit circle, you just a second, I'll try to make sure everybody's muted. Okay, and this one, you can take any point in the complex complex space, right? And start basically spinning this around with a Z. So of course, if you're in a unit circle, you'll be making these phasor spins. If you're inside the unit circle, you will be basically spinning with a spiral down to 0. If you're outside of the unit circle, you'll be spinning out in a spiral that goes to infinity. But this is kind of the same idea. And by writing it this way, it actually looks like a polynomial in the Z space, right? These would be the coefficients of the polynomial. These are the powers. Especially if this is a finite number, then you have a finite order polynomial. And then a lot of signal processing deals with finding the roots of this polynomial. And these things will have meaning when we start talking about speech and vocoders and formats. If you represent them as filters, these things will have really kind of very neat and something elegant representation of areas where the filters basically give more or less energy in the frequency domain. But this is more like a motivation. At this point, really what I want you to notice is that this is really one-to-one, except for this is much more general than this. And a convention that we'll show in the next slide. And this is that if we do this z minus multiply the Fourier transform by this number z minus 1, so at this point it's really just a math thing, it will correspond to the z transform of one sample back. Just by adding here minus 1, we shift all the n by 1. So this is why many times people in the signal processing literature refer to delay of one sample as z to the power of minus 1. So yeah, so this is kind of a jump a little early, but that's exactly the point I want to kind of start moving next. What is a linear filter? So the original linear filter is an idea that you take a bunch of coefficients or amplifiers. So these little triangles are gains, and the number, the B0, B1, B2 are just different values of these gains, they're real numbers, and a bunch of delays. So we explain why z minus 1 is basically a delay. It's a one-step delay. And this is an implementation of a linear filter. Mathematically, it's actually written this way. And let me kind of briefly explain what is the relation, why this is the same. So what happens is that we have a signal coming here, okay? The first sample will be basically multiplied by B0, okay? And if there's nothing before that, it will move to the output. Then one step after, that first sample moved here, and the second sample comes in here. So the first sample now will be multiplied by B1, the second sample by B0, they'll go out. And as the signal progresses, after n steps, you have the first sample multiplied by Bn, the second sample by Bn minus 1, and the sample which is delayed or n samples later will be multiplied by B0. So, oops, jumping a little, trigger happy. If you check and try to see how this process is mathematically represented, you will be seeing this equation. The only kind of thing to notice that it kind of assumes that the signal existed from minus infinity to plus infinity, but B is usually a finite number. It has so-called, these numbers B are often called impulse response. We are not going to go too much into what impulse responses are, but you can think about the idea that if you just bang here with a 1 and the rest is 0, so as this 1 propagates, it will reveal the B0 at sample step 1, then there will be 0 coming here, 1 will move here, you'll have B1 coming out, then the 1 will move here, everything else is 0, so you'll have B2 coming out. So if you replace the x of m with a signal that is 0 everywhere except for 1 at position 1 or 0, whatever, and you can define your indices as you wish, but there's just one point in xm where there is a sample of 1 and the rest is 0, you'll get the b's out in that sequence. That's why it's called impulse response. And you can show that if you know the impulse response of the filter, you can actually calculate mathematically the response of the filter to any signal, which is kind of pretty evident now. You can kind of realize that if you don't know what the filter is, you slap it or bang it with the impulse response. Now you see the B's. Once you know the B's, you can like take a new signal and mathematically calculate what's going on. So this is really a linear filter. Why it's called linear? First of all the operations here are linear. There are sums and multiplications, but because of the nature of this way the filter operates, you can see that it also has linear properties as a function, in the sense that if you take two different inputs, okay, you have x1 and x2, and you filter each one separately, you'll get two outputs. If you add the outputs, it's the same thing as providing in the input the sum of x1 and x2. So this is a linearity. So the result of the filter, so linear combination of input becomes linear combination of the outputs. Some other properties of linear filters are that they don't add any frequencies. We'll show, and we'll talk about this a little bit more in a minute, but they may change the amplitude of sinusoids, but they will not produce new sinusoids. And this is also a very important property, because if the filter is nonlinear, you might end up the filter itself generating new frequencies. Linear filters do not generate frequencies. They can suppress or they can boost frequencies that already exist in the signal. So, I mean, this one maybe doesn't, the basic math here doesn't immediately show this, but we'll talk about this in a second. So this is a linear filter, and normally it was implemented in circuits that actually would implement delays and little amplifiers here. Okay, so this is just a visualization of the convolution, the equation we had on the bottom. What we have here, think about, and because convolution is kind of symmetric, you can decide what is your X and what is your B. Okay, but in this case, let's think about the triangle as the fixed one, as this black line will be our filter. And the way it's represented here, the numbers, so think about them as subdivisions. So it's actually 1, 2, 3. It's not exactly the right way to think about this. You have many more indices here. Okay, so these are the samples of your B, and let's say your signal X is this boxcar moving. Okay, so you can see as the signal passes through the filter, it actually triggers at any point a sum of all of the filter coefficients that actually are under that box. And if you do the calculations, this will be the output. So the red one, Y, is a time signal, which results from filtering the green signal with a filter that has the impulse response, the B's, as this black triangle. That's kind of the essence of a convolution filter. Now the linear filter and the convolution operation. I guess some of you at least have heard that convolutions are today pretty popular in the visual domain. So all the CNNs, the convolutional neural networks, usually implement filters which are more than one dimension. This is a one-dimensional convolution. In that case, you also have like a finite sum, and instead of delays, you basically have some kind of a configuration in space that actually averages over a region, sums them together, and outputs a value. This is really exactly the same idea, the same operation, just that in images, you don't have delays as such. You have really indices which represent positions like a neighboring region in an image. So you have like maybe 3 by 3 region, and you have somehow to index all the pixels there. While here, the delays in some sense serve as shifting the index of the signal that you're going to process. And the black one is really your fixed filter that now actually moves. So you can think either as the filter moving through the signal or the signal moving across the filter. In that sense, this is kind of whatever interpretation you want to choose. I mean, the result will be the same. So one important thing about the convolution theorem, because we're talking about frequencies, is the following, and I just provide here the result, and the proof is pretty straightforward. I might mention this briefly, but here is the essence of convolution theorem. What we find, what turns out if you do the math here, is that if you take two signals, two time series basically, they're all discrete, and you perform the convolution operation. So this star is usually denoting convolution operation. And again, here it's not clear which one is the filter, which one is the signal. You just take two sequences X and Y, and you convolve one against the other, and you get a new signal, okay, the output. So the Fourier transform of a convolution output is a product or a multiplication of the Fourier transforms of the first one and the second one. And this is really a powerful result because it somehow makes sense that what we have here is actually a frequency representation or characterization of what a filter does in time. And what happens with a filter is that if we know how the frequency representation of the filter, let's say y is the filter for this, for the purpose of this discussion is, if we know how the frequency response of y, how it looks like, we can now take a signal x and we can shape it in a multiplicative way by actually in the frequency domain, we'll be basically scaling the frequency of x by this factor y. One caveat or one point here is that the actual math here assumes a complex product. So you basically multiply components, element-wise multiplication between all the frequencies. So if x is our vector with x1, x2, xk, whatever our FFT or DFT size is, and y is the same DFT of y, we actually multiply them element-wise. So we multiply the amplitudes, but we also have to multiply the conjugate, so we get also the phase. So filters have phase, which might influence the phase of x. For those who are not confident really still what the meaning of phase is, we mentioned it several times and we said always that we ignore it. It's just that it exists and we need this to invert the signal. So I'll continue with the same logic and say, yes, phase exists here. We will most often ignore the phase, although it still affects the signal. So if we just think about the amplitude aspect, this is what is represented in the next graph. Filtering a spectral multiplication. So this is just a snapshot from a filtering plugin in a digital audio workstation. And usually, these plugins have nice graphical interface. You can drag and kind of shape your filter. So if this is your filter, and so let me explain what we are seeing here. These are frequencies, okay? And you see this is like in kilohertz. So we have a signal because it's usually audio workstation. So you have it, well, if this is 10, I guess this is 20. So it actually has the full hi-fi bandwidth. So this is your frequency axis, and this is your amplitude axis in dBs. I hope you can see this slightly small. The fonts are small, but full screen you can definitely see this. So dB is just a logarithmic way of computing, or the units for amplitude. It's 20 log of the amplitude. We didn't explain why exactly dBs are computed the way they are, but just thinking about them as amplitude scale to some logarithmic scale. So this is how strong the energy component is at every frequency. So what we see here, I don't know if you can see this kind of, there is this like, well, black here, there's this kind of a dark brown and light brown. You can see there are some wiggles here. So this is your original signal spectrum, okay? And what happens is that this filter would be a low pass filter. Why it's low pass? Because it lets all the low frequencies go unchanged, unaffected. And then from a certain point on, it starts basically multiplying. So this is where the multiplication comes in. You basically scale your original signal, this one is shown in the light gray, by this number. You basically multiply your original amplitude by this number. So as this number goes down and down, you see that this is the white line here going down is actually this light gray line, not gray, but like the light brown line here, just kind of scaled down. It actually even has the same shape. So what the filter did, it took an original signal here, it didn't change anything. And as this curve started kicking in, this white curve start basically taking that hardly seen the light gray curve and scale it down, bring it down according to this this multiplicative factor. So this is what actually this theorem tells you, is that if you want to design a filter, you can think about designing this in the frequency domain, and you might also understand it better, or when you listen to the filter, and you know that you want to remove high frequencies, you would hear them accordingly. Or if you want to do a high pass, or you do band pass, or any kind of an equalization operations, of things that you might do when you change, the settings in your car audio system to get either the high end or the low boost. You would normally operate with something like a filter. You might just have some buttons instead of a continuous curve, but this is the effect. Just the last quick comment is that because of the FFT, because the Fourier transform operations were done so effectively, many times now actual filters are implemented in the frequency domain. It's easier or cheaper to take a signal, make a Fourier transform, have a filter stored as Fourier coefficients, make the multiplication in the frequency domain, and then make an inverse Fourier transform, then go back and implement this in time with delays and multiplications. But this is kind of part of more of the engineering aspects of implementing FFTs, signal processing like vocoders and things that process speech that used to be done with filters in the time domain are often done in the frequency domain by doing an FFT first, just because it's much faster today. So this is pretty much, that's the end of the filtering lecture, and I will move to questions.